using the array of 3x3 coils. You can do this with simpler mass manufacturable pieces of hardware in arrays of HTS. And that's when we'll take a next step to start working towards an integrated machine.
Hello and welcome to Next Big Future. I'm very pleased to have Brian Berzin, CEO of Thea. They're a nuclear fusion company working on stellarator, and they just got $20 million in funding. So I'm glad to have Brian here and to talk about what Thea is doing and how their method will get us to commercial fusion. Welcome, Brian.
Thanks, Brian.
Yeah, so why don't you tell us about Thea, the funding you got, the work you're doing on stellarators, and how that's going to be beneficial.
Yeah, sure thing. So Thea Energy was founded in April of 2022, so 2 years ago. We are focused on commercializing the stellarator. The stellarator is one of the oldest forms of magnetic confinement fusion, actually dating back to the early days of Princeton Plasma Physics Lab, PPPL, one of the legendary DOE-funded national labs, which we spun out of. So the stellarator, a form of magnetic confinement fusion, has a very complicated coil set that makes a very complicated plasma shape that looks a bit like a French crawler. And there were some really special and I'd say meaningful breakthroughs on stellarator theory in the 1980s. And it took about a couple decades for that to actually make it into practice. And that was W7X, a large-scale integrated stellarator that showed quasi-symmetry, this optimization technique that confines a plasma, the fusion fuel, within a stellarator very, very well. And the reason it took so long to make that system is one, because the theory was incredibly complex and the computing requirements were incredibly complex. But then you had to transfer all this into an incredibly complex piece of hardware. And if you've ever seen a picture of the stellarator in these kind of wiggly shaped magnets, that has been the Achilles heel even since W7X was put online, because these are, I think this is the rule of thumb for fusion, but all of hard tech is building hardware is indeed, costly and takes a lot of time. So where Thea comes in and the breakthrough that we had that said, okay, we should spin this out and we should really focus on commercializing this new type of technology, is a way to reduce the complexity of the hardware and to reduce the precision requirements of the hardware. And we're not eliminating the precision, we're not eliminating the complexity, but what we are doing is we're transferring it to a control system, something that is inherently scalable. If you build a control system once for one magnet in our array, the same control system works on the 1,000th magnet. The way I like to think about it is an array of pixels on your screen right now. Why you can see my face is because every single pixel is controlled individually. And the other side of this is for a stellarator, we now use an array of HTS magnets, and every single magnet is controlled individually, and therefore you can create the highly complicated, that very specific shape of the stellarator. So Thea, 2 years old now. We have about 35 employees. We are headquartered right outside of, and really that was core to our story of spinning out of the labs. Our first, call it 10 employees, were part of the lab and worked on stellarators for most of their career. And now we're really bringing best of class aerospace engineers, HTS magnet engineers, mechanical engineers, and electrical engineers at the end of the day, people that exist at a lot of these deep tech companies. We're prototyping our magnets. And the cool thing about our magnets is that the cool thing about our approach and the work that we're doing right now is iterating our tech, iterating our hardware. These are things that are, I'll call it, you can fit on the size of your desk, these smaller magnets. And that gives us a real programmatic advantage where we can just iterate so much quicker on our technologies versus the status quo of fusion. Status quo of fusion are, systems and cost millions of dollars and take years to build a single one. So our building block, our Lego block of our technology is these planar coils. And we're iterating on them very rapidly, even month to month now. Yes, we're going to need an array of a few hundred of them, but knowing that we can perfect the building block in terms of its performance, in terms of its manufacturing at scale, that's what we're working on for the moment. And I call it towards the end of the year is when we're going to hit, I'll call it a pretty significant prototyping milestone where we're going to operate an array of HTS coils, a 9 by 9 grid. And what that in essence is your controls problem. If you have one magnet surrounded by 8 others, they're coupled via inductance. So if you can do it, and if we can show that we can make that highly complicated, highly precise magnetic field that's required for the stellarator using the array of 3 by 3 coils, it's the same control system for 100. So that's the milestone that we intend to hit later this year, towards the end of the year. And that will be a milestone that really indicates that you don't need the wiggly coils. You don't need the very complicated, very precise, very expensive modular coils of prior stellarators, that you can do this with simpler mass manufacturable pieces of hardware and arrays of HTS. And that's when we'll take a next step to start working towards an integrated machine that shows our technology at scale, that hits some, let's say, pretty significant performance milestones. This is a system that would be on scale and class of the largest fusion prototypes of the world. And yeah, quick little soundbite on our Series A. Prelude Ventures out of California led the round with participation by Lower Carbon, a couple other of our seed stage VCs, and Hitachi Ventures joined the round as well, alongside Anglo American and Orion Resource Partners. These are three that I highlight because they come from real assets, mining, and Hitachi building power plants across the world. So we know that that's where we are going, and we're glad to have some real strategic support that know how to do these things at scale.
On the tokamak side, Spark Fusion, which is the MIT group, they were working on mass producing superconductors themselves at the 20 Tesla level, which is about more than the 8 Teslas that the traditional main international tokamak project was previously working on. And now we're going to more powerful magnets. Those involve a lot of tape, like the superconducting wire of the ceramic superconductor. They made something very large, about 10 feet by 6 feet, if I recall correctly, with the size of one of their magnets.
Yeah, that's coil. Yeah.
And they bought 20 of those. So you're using a coil set of magnets. What's the size? And you said lower cost. So how much lower cost are we looking at there?
For us, compared to some of our peers in terms of use of HTS and overall magnets, I'd highlight just one thing very quickly, which is the HTS tape that we purchase from a couple of vendors across the world, as well as our peers. We are not producers of that HTS tape, and most other, I'll call it fusion technology companies that are looking at a specific architecture, a stellarator or a tokamak, they're not producing that tape either. They're buying it from, I'll call it an entirely different nascent industry that's emerging, producing HTS tape, which is a pretty fascinating thing to watch and witness that scale. And that's great because we need more of it. The entire world needs more of it. It's a really, really special thing that allows you to pretty much take a copper wire that would be an inch plus thick and run it through a piece of tape that's 4 millimeters wide and paper thin. So it's a big deal for fusion because it means we can build smaller, stronger magnets, cheaper magnets, more efficient magnets, and it will also revolutionize many other industries, including transmission. So we, similar to our peers, take that HTS tape, but that's when things are started to be done a little bit different, maybe our approach versus others. One of the just overall paradigms that we get to work with is the efficiency of the stellarator. A stellarator is magnetostatic, so you make the magnetic field in that wonky shape that has the twist in it. It's very happy in that shape. And because of that, you don't pose the risk of disruption, and you don't actually have to recirculate a tremendous amount of energy. All fields, including the poloidal field twist, I'll call it, it's in the system itself. In other devices such as the tokamak, where it's symmetrical like a donut, you need that twist. The E&M principles show very quickly that you need the twist. It's Ampere's law. But you have to drive it. Because the system's symmetrical, it means you have to push that twist into it. So you put a center solenoid in the middle, and you put a poloidal field coil set that goes around the long way. They're really big. That's actually, not just a big use of HTS tape within the system. It is, you have to recirculate a tremendous amount of energy. And so I think right off the bat there, you have a need of HTS tape that's been removed, and a recirculation of energy that's also removed. And because of that, and we want to go to high field, to be clear, HTS allows us all fusion approaches within magnetic confinement to go to higher field. I mean, you can have a bigger ball of plasma and a smaller device. You can have different types of efficiencies and cost benefits. But for us, and I think this is a role that I have across my years of different types of hard tech and my team's experience across different types of hard tech, ranging to aerospace, is that when you start to push the bounds of a certain engineering system or subsystem or material or structural forces or cryogenic systems, whatever it may be, or multiple of them, that's when things start to break. That's when extreme precision becomes very expensive. So for us, compared to, I think, what HTS is capable of, yeah, it's hugely impressive that HTS magnets can be made to go to 20s, even 30 plus Tesla. But that's when all these other parts of stress, cryogenics, inefficiencies, what have you, start to creep in. So we are believing in an approach a little bit more of moderation. And part of that is because the Stellarator allows for it, because it is very efficient and it doesn't have these risks of disruption. So because of that, our magnetic fields at the magnet coils are in the teens, 12 to 16 Tesla. That's a substantial amount decrease from what I think the max field of HTS is, and it also gets to take advantage of different temperature or current paradigms of the actual HTS. And because of that, we get to deal with some different types of efficiencies for cryogenic systems, for instance. Cryogenic systems are much more efficient at higher temperatures. We have much less structural stress on a number of our components, and the tape is less prone to error. So for us, that I call it, we like to think of that as some practical real world engineering that we can bake in. But it extends to economics. It extends to the type of tape we get to use. It extends to the cost of the tape. And so for our system, we do have two coil sets. One are large encircling coils that make the majority of the TF field in the long way. They actually do some of the shaping of that very specific plasma shape as well. Those look very similar to tokamak coils. They have, so not quite those. Ours are planar. So they exist in one plane and they're fully wound in tension. So they really look like TF coils from a tokamak. Okay. And then the second set are the coils that fit on your desk that are slightly bigger than a laptop, that do that really last 10% of the fine tuning and the shaping of that specific shape of the Stellarator. And those two coil sets are our core technology and our intellectual property. And this was a pretty interesting part of the story around our founding, is when we put in a provisional patent and took that provisional and put a full patent application in, and we were looking at kind of, I'll call it prior art and what exists out there in the world. And we kind of very fortunately came to the conclusion is, wow, we have complete freedom to operate here. And we have a very broad IP scope that we now have coverage on. And that's because the planar coil Stellarator idea, without the control systems, without high field magnets either, it wasn't possible. And part of it, no one thought of it until now. So it allows us to have a really, I think, thoughtfully designed system that scales well to a power plant, because now we can fine tune out within a control system error of hardware. And it could be from the wear and tear of a system. If you're running a system and the magnet is on it for 10 years, it's probably not going to be operated at peak condition 10 years from now. And any other Stellarator device before, if you have imprecision or a broken piece of hardware, the entire system doesn't work. We have a control system on top and a knob, and we can turn magnets up or down because we'll have the instrumentation to know exactly what's going on. So that allows for this, I think, real world practicality of, okay, if magnets are different, one being newer than the other, or one literally being made by a different manufacturer of HTS tape, or what happens when it's put together, and it's going to be put together by human beings. We're imperfect. What happens if we mount one of the magnets a millimeter off axis? That would have been catastrophic to any other fusion device before us, but now that's just another variable to tune in the control system. So having this layer of the control system on top means that we can take advantage of just these recent massive breakthroughs in machine learning in other places, because having 1,000 input output variables is actually not just an easy problem, but it's a benefit. It means that we can actively control for things.
So what's the so for get people familiar with this, so both the tokamak and the stellarator are trying to contain hot plasmas in the 100 million degree range, right? And for deuterium tritium fusion, which I presume that's what you're doing, right?
Yep.
And so the different kinds of hydrogen with two or three extra neutrons, I guess is what it is for the different materials. Deuterium being two and tritium being three, and the problem has been stability of this plasma material at this high temperature. The longest on the tokamak side, probably like a couple of 3 minutes, is how long they've held the material stable. Stellarators have been able to hold, I'm not practically, but in theory, at far longer times, more stable, but they said more complicated thing. So the control system need to react within milliseconds, microseconds. What's the time frame in terms of the instability that they deal with?
This is a pretty in-depth subject. So I'm happy to cover it though. So I'm actually going to handle this in two different steps. I'm actually going to spend a brief moment talking about the tokamak. And my co-founder is David Gates. He was the department head at PPPL, where he focused on international collaborations and for the Stellarator. W7X and LHD were among his collaborations. LHD actually has, I believe, the record for longest stellarator plasma. W7X also has shown increasing pulse durations. And actually, I believe the limiting factor for W7X is the cooling capacity. It could perform for longer, but they shut it off because it doesn't have the cooling systems to extract the heat for longer than a certain period of time. So it's actually the system hardware that is the limiting factor on the back end. But before David focused on stellarators, he was focused on the tokamak for 10, 20 years. And part of that's because stellarator projects didn't exist for a while. The stellarator was squarely in the backseat until some of the breakthroughs of quasi-symmetry that I mentioned before came to be. So at the beginning days of David's career, he worked at Culham in the UK and on a couple of tokamak systems at PPPL. And his specialty was actually in the control systems. And so to your question, the control system that's required for a tokamak, because of plasma in a tokamak, is MHD unstable, which means that you very specifically have two of the poloidal field coils, the big ones that go around the outside, kind of around the crater. You pretty much, you take two on opposite poles, and those are fast response coils. They have to, on a millisecond time scale, bounce the tokamak plasma up and down so that you contain it in a certain way. So the math that's required for that is it's a lot of math to compute in a millisecond time scale. But tokamaks do it, and tokamaks have done that since, call it, the 1980s. So that box is checked. It's a feat of science and engineering in itself there that they were able to do in the 1980s before computing's anyone like it's today. But you can absolutely control a tokamak in nearly real time on a millisecond time scale. For the stellarator, and even with 1,000 input-output variables, or even for a traditional stellarator like W7X, the time scale required to control a stellarator is much lower, actually. And that's because it is magnetostatic. It's not unstable. It is very stable in its little paradigm. So when you want to train, for us, when we want to change a parameter on our system, and maybe we want to change some of the individual kind of tiles of those planar coils, that will be done on the minutes time scale. Mm-hmm. And that's a big part of there's no risk of disruption in our stellarator, in our plasma equilibria. So it will not all of a sudden lose stability and have the energy that's in the fusion plasma deposited on the wall. For us, if you do lose confinement in the stellarator, and I actually believe there were a couple experiments at LHD over the past 10 years on this, where they purposely tried to make a stellarator plasma disrupt, the plasma just loses confinement. And you can start it right back up again by having a gain confinement. So it's a it's not a destructive process that could break the system, but it's also very hard to do. And so we have time on our side here. And if we want to change parameters, let's say we want to heat the plasma up and ramp it, or maybe we want to load follow for power plant, that is a process that happens over the course of minutes here. It's very slow.
Okay. Because for those millisecond adjustments on the tokamak, they've only added up to like, 10,000, 20,000 before the thing falls apart, and then they have to shut it down. So, so you mentioned you'd have achievement over by the end of this year or early next year, where you'd have your 3x3 array set up, and then that would be a proof of concept that the replacement of the more complicated magnets would be possible. Then you can go to a full scale system after that. Is that the general plan?
Yeah, that's right. So this project actually was founded out of an RPE beta, BETHE program from 2020 to 2022. And that program set the basis for this and actually had some prototyping, but with permanent magnets. That was a great first step because that showed, not just in theory, but actually building out some of the permanent magnet slices, that you can make these highly complicated magnetic fields required for a stellarator using simpler column dipoles. Permanent magnets have two downsides, though. One, they're always on. And two, permanent magnets, even the strongest ones, can't go to very high field, not high enough for commercial fusion, for DT fusion. That's when we said, okay, we're making the switch to HTS tape. Very fortunately, the theory was just a very clear extension of the bedrock foundation that we had then. So we had a very strong theoretical basis for showing that this does work. And now we're taking that next step where we are prototyping, and we're going to have call it the experimental verification of an array of HTS magnets, making that complicated, precise magnetic field that's required for the stellarator. And that, in essence, is the one new thing that we're bringing to the stellarator. When you talk about the other subsystems of how you fuel a plasma, how you heat a plasma with gyrotrons, some of the cryogenic systems, we're not proposing anything new or anything past the state of the art for tokamaks and stellarators alike. The one and precisely one new thing we're bringing to the table is taking out the modular coils, replacing with them an array and a control system. So that's exactly what we'll be proving out with this milestone around the end of the year. And then we'll take the next step of starting to work on an integrated system based on this planar coil architecture.
And then, so the rough timeline for that, assuming you hit the milestone at the end of this year, right? Then you'd have to go through more follow-on fundraising before you can go on to a full-scale prototype, I presume, right?
Yeah, we're very fortunate that our investor base already, the names mentioned, Prelude, Lower Carbon, Hitachi, they're funding us knowing what is coming. We want our investors and even the broader community that we work with, including our employees, to fully understand the steps that's required to commercialize fusion. So prototyping is the first step, the near-term step. After that, yes, we will be raising more money to build an integrated system. And this is where I'll call it two steps happen. Building an integrated system that we own and operate. And then the step after that, a commercial first-of-a-kind pilot plant, if you will. That system will be owned and operated by a utility, an end user, an owner-operator, whoever that may be in the world. That's really where a change in business model will shift. We're not going to be a utility when we grow up. We're not going to be an owner-operator. We're very good at the fusion technology. We're going to make the fusion island, the main fusion systems that will be integrated within a larger power plant system.
In terms of so it seems like much of the proposed development is relatively defined. That basically, if things work, you're at this 15, 16 Tesla range. The size, the number of magnets would be known because if the control system works, then you have 9 times more magnets than some previous systems. So you have a few hundred of these magnets. And the cost of those magnets is known. So then the size of the system, previously at So one of the drawbacks, I think, of the interactive tokamak is that one, that whole project has been going on since the time of Ronald Reagan when he kicked it off some few decades ago, and then now it's hopefully going to get the time kept slipping to when they would get to their initial plasmas, and that's now in the 2030s, I believe. But that whole system would not get to commercial fusion. That would basically be the beginning of proving something for tokamaks, and then we follow on by demo, and then for a
Yep.
full commercial system. So basically, for people who say nuclear fusion is always 20 years away for international tokamak, and the follow-on project is more like 40 to 60 years to never away. And also, one of my problems I have with that is that the demo system, the follow-on near commercial scale, would be the size of a baseball stadium, professional baseball stadium. It's just like
Yep.
freaking huge.
Yep.
So what would be the size and the economic roughly of what you're looking to do? That's the whole point, is to get to commercial
Yeah. Yeah.
power.
Okay. I'll make a couple points before I get to the conclusion and answer your question. But just stepping back a second I'll call it this wave of private fusion, privately funded fusion. A big part of our story that I think I mentioned at the beginning was spinning out of PPPL, where the Stellarator was invented. That took 70 years from the start of PPPL, when Lyman Spitzer invented the Stellarator, to when we spun out. And we're the first spin out of PPPL that's concentrating on commercializing fusion energy. And I'd argue that we were not a day too late and not a day too soon. It took that long for the science and the theory of the Stellarator to get to the point that it was ready to shift to the commercialization stage. VC and private investment, that they do not fund scientific R&D. That's what academia, that's what national labs are there. They're very good at funding past the bleeding edge, where you can't necessarily justify it via a return of investment, whatever it may be. And then you get to a point where you have a firm scientific basis, where I believe the tokamak and the Stellarator now sit. And that's when startups and private funding, where we're really good at commercializing, not just, I think, what we're doing in fusion now, but you look at other industries, look at NASA COTS, which I'm going to hit on in a second. The private industry is great on taking something that has a firm scientific basis and figuring out the engineering of how you commercialize this, how you sell it, how you do it so efficiently. That's where fusion is getting to right now, and I believe that's what our approach does for the Stellarator. There are a couple of things going on across the world. You mentioned ITER and potentially the follow-up of demo. No, that's an integrated project that's focused on some science that is using some technology that is, I call it, as you mentioned, fairly dated. And therefore, yeah, there are some technologies that are falling out of it that we will all benefit from. But in terms of the commercialization effort, yeah, I don't think it's fair to look to a government-funded project as the leading source of commercialization. And this has already happened, where the private industry, even before Thea was founded, you look at what CFS is doing, has absolutely lapped that program. So for us now, and this is the first time ever as of about a year and a half ago, 2 years ago, there's a program being funded by the DOE, of which we are an awardee, that is a cost share, public-private cost share, supporting the commercialization of fusion within private companies. So that was modeled after NASA COTS, the program that really led to the creation of SpaceX. So I think there are starting to be some even government-funded initiatives that really understand that the private sector is focusing on commercializing fusion and ultimately going to be the ones that do it. For us and our technology and where we're going, we need that firm scientific basis. The Stellarator, I think that box is checked. We want to focus on a system that can be built practically. I think we have that with the planar coil Stellarator. Another thing to mention before I get to your point of what a power plant is going to be and what the size is our platform having this array of planar coil magnets, and even a maintenance scheme. We can remove entire chunks of our system. That allows us to take advantage of future technological breakthroughs and advancements as they come. Call it AI and ML on the control system side, call it better HTS tape or better first wall materials. we have a platform with a modular architecture that is assembled in components and chunks and sections that we can absolutely add onto and take developments and add them into the mix as we go here. That's a big part of going from a first of a kind power plant to an nth of a kind. That's very efficient. That's more affordable. That can be made quicker even. Our system is going to be a few hundred megawatts. We believe that the first of a kind pilot plant will be about 250, 300, and an nth of a kind will be closer to 350 megawatts electric. Part of this is just fusion works better bigger. It's the ratio of surface area to volume. It's the laws of thermodynamics at its truest form. That doesn't mean that we want a system that's the size of a football field. That's when engineering complexities and even programmatic risks take over. So a difference between our approach, that system, nth of a kind power plant making 350 megawatts, that system is about a 5-meter major radius. So it's a bit like a bike tire. It's not necessarily like a big ball of plasma like you might think of a spherical tokamak. It's a bit more like the bike tire in terms of an aspect ratio. But still, the capital cost of that system is closer to $1 billion, not 10. And I think that 300 megawatt electric output and $1 billion capital cost are going to be real sweet spots for fusion. I think the economics of fusion below that, if you're talking about like 100 megawatt power plant for at least magnetic confinement, does not necessarily pan out because, and especially for the Stellarator, we get to take advantage of something called ignition. Not necessarily what you think about with the NIF announcement, but the ignition that we're talking about is having a plasma that's self-heating. One of the real cool aspects of the Stellarator, I mentioned that magnetostasis before. That steady state behavior means that you turn a plasma on, you'll continually fuel it, grams of fuel, not a significant amount. As long as the plasma keeps its confinement via the superconducting magnets, that your plasma will be self-heating via the DT fusion process. That means that as you heat it, you're pumping in megawatts of energy. When it hits ignition, you get to pretty much cut that input off, and you just get a tremendous amount of energy that you can convert to electricity. At a subscale of going below a certain meter radius, which means that a certain ball of plasma, it becomes impractical from a physics perspective to have, call it, 100 megawatt electric power plant. The energy balance of that ignition works so much better at 300 plus megawatts. On the flip side of that, though, building a system that is a gigawatt scale means that you need just massive pieces of hardware, things that are the size of houses that you can't transport down a road at all. Mm-hmm. That's, I think, one engineering constraint. And the other that I think fusion will start to wake up to and take note from fission and a couple of other industries is just the programmatic risks of gigawatt scale facilities when it's just dollars and time. If you have a gigawatt or 2 gigawatt scale power plant and it goes over budget by 2x, that bankrupts a company. And if it takes 10 years instead of 5, that project is dead. The programmatic risks of large systems just snowball. So I do think that overall having smaller overall systems, call it 200 to 300 megawatts, is less programmatic risk, better, can be closer to demand, can work in parts of the grid across the world that maybe the grid is not like the United States. I think that's important pieces of the puzzle as well to think about through the commercialization of fusion.
For the fuel, there is a limited supply of tritium, which is not tritium does not occur in nature. It has to be produced. There's only a few, I think 20 kilos of tritium currently in the world, generally coming from the CANDU nuclear fission reactors. So there has to be, I guess, a generation of tritium within the reactor and then some kind of harvesting mechanism. What is the method that you have for that?
Yeah, that was an important thing that we considered across my fusion career when I started at General Fusion about 2017 and really wanted to make as a main focus of Thea when I founded the company with Dave in 2022. We, with our first system, which will be, we call it EOS, it's a neutron source stellarator. It's not a power plant. It's not going to put energy on the grid. It's going to be subscale in that regard, but it's going to use our planar coil technology. It's going to be a fully integrated system. It's going to have a blanket even. It's not going to be a DT fusion blanket. It's going to be a DD fusion blanket. And this system actually will utilize a technology that was developed for ITER called negative neutral beam injection, NNBI. And it's actually how JET made a substantial amount of its fusion yield. It's beam target fusion. So for us in our stellarator, we can achieve very high confinement of a plasma these days based on our optimization. And so we can inject fast particles above the DD fusion threshold. Mm-hmm. And by doing so, we can drive a DD fusion within the system in steady state, as uniquely as Stellarator is. And we're going to use that within our first device to actually breed tritium. And for us, this checks a lot of boxes. It shows our technology in an integrated fashion at scale. That will allow us to go after the next step of putting a pilot plant on the grid. In addition to that, it will be a commercial system, though. It will not just be, a science project and a press release and milestone achieved and the system is really useless for everything else. We want to then operate the system long-term to produce tritium, because to your point, we have absolutely realized that the tritium supply chain for fusion is not there. And I think this also makes all of our lives in fusion easier, because if we can make EOS, if we can build this tritium neutron source that breeds tritium via a DD reaction, so no tritium required on the input, half of the tritium, will be made just via DD. 1 out of 2 reactions happen, one leads to a triton. About half of the tritium, the other half will be bred in the blanket. The blanket will use lithium carbonate. It's one of the more easily accessible forms of lithium. It's actually a medicine. We're going to build blanket modules out of lithium carbonate, and we'll breed tritium in those. And because of the system having a source of tritium, that for us, and I think the entire industry, allows a relaxed constraint for the first fusion pilot plants. For us, for any of our peers, to put a fusion pilot plant on the grid to produce electricity is going to be a feat, and a lot of good engineering is required for these systems. Let's be clear here. There are big challenges that we all face for blankets, for first walls that have to deal with a 14 MeV neutron flux. They're going to be real impressive machinery. If we can use a tritium neutron source to relax one of the engineering constraints for a pilot plant, I think we'll all be better off. And that is tritium breeding ratio. If we can make tritium over here using a Thea neutron source system, that means for our pilot plant, our first of a kind pilot plant, we can not have to worry about one thing. We can make it a better power plant. We can say, okay, we can not have to crank the tritium breeding ratio up, because every time you crank the tritium breeding ratio up, or you're focusing on breeding tritium with a certain type of lithium or a certain type of blanket, it means you're making a worse power plant. It means you're having lower efficiency, or you're making some engineering compromise, or likely many. Mm-hmm. So our goal here is to supplement the tritium source with our first system, EOS. Therefore, we can focus on having a little bit better of a power plant when we take that step. And I think that's going to be good for our technology as we take that step. But I think it'll also be good for the entire industry when potentially there are more types than just one fusion power plant being put online.
So one, for people who are not as familiar with the nuclear fusion industry, that statement that you described there of creating a tritium breeding out of DD is very exciting. So DD fusion is at 300 to 400 million degrees, if I'm not mistaken, which is less than what is needed for proton boron at 1 billion degrees. So there's different kinds of fusion, those 3 main kinds: DT at the 100 million degrees, DD at 300, 400 million degrees, and then proton boron, PB, at 1 billion degrees. So the fact that you're going to be breeding that, so what will be the time frame to that? One question, one. And then two would be, there's a value of a neutron generation system, if like what nuclear fission, nuclear industry would call a neutron economy. That if you can make your neutrons cheap enough, one in the nuclear fission side, you can if you can use those neutrons to say split even numbered um, uranium, 238 being the main kind of nuclear waste, which you can then close the nuclear fission cycle if you were to generate that. Is that something that's possible on your end, or the speed of the neutron is not the right level?
We're contemplating a number of these things. Tritium is number one on the list because it is required for the next step that we're going to take, putting a DT fusion system on the grid. I'd say that the second potential use case that we're contemplating now, and even having some conversations with potential end market users or customers, is the medical isotope community. Yeah, you're absolutely right that the neutron source is the limiting factor for a number of technologies that exist in the world, whether it's breaking down long-lived radioactive waste or the creation of medical isotopes, some of which are really important to the medical community for treatments. But they do rely on largely a fission-based neutron source. So there's significant cost burden and significant regulatory burden for getting those. And because of that, extremely supply limited. So we believe that our neutron source could potentially be capable of helping that market as well. Our system in the first iteration of EOS, we're going to have kind of almost 12 slices of the cake. And we therefore will have the opportunity to, over time, change out blanket modules. So initially off the bat, we're going to focus on a lot of diagnostics to verify our performance, to show that we can create a plasma and confine it and change parameters and work under all these different types of conditions. And then over time, we will add in blanket modules that will breed tritium. And then potentially after that, we could add in a blanket module that focuses on a certain radioisotope for a specific type of treatment for the medical community. There's no reason why we couldn't consider other use cases as well. At that point, though, there's no reason why we couldn't just build another neutron source stellarator. If one of the national labs of the United States wants to build one to focus on developing technologies to break down certain long-lived radioactive waste, why not? We could absolutely consider that. I think that might be a second system, especially when you consider that all the non-recurring engineering and the first of the kind is already created. Building a second EOS probably is going to be significantly easier, cheaper, faster. So you could, there's no reason why you couldn't have a fleet of these systems at one point.
Mm-hmm. Yeah, because in terms of closing the loop on nuclear fission, the pyrolysis systems that France and Japan, they recycle about 10% of the 70,000 tons of uranium that goes into nuclear fuel each year. So about 7,000, 10,000 tons of that gets recycled. And those recycling systems are massive plants that cost like, $20, $30 million a piece. So massive amount of cost in that thing to do that. And then on the nuclear medicine side, there's multi-billion-dollar a year industries on the nuclear medicine side. And that's, as you say, a constrained level. That if we had more cheaper of it, it would be a better medical system for us to get those kind of materials to get scanned. Yeah.
Especially if you can do it with fusion, not fission. If you can build a fusion system as a neutron source for creating medical isotopes, you can do it without population-based risks, without the risk of meltdown, with minimal risk of proliferation or weaponization, and with no long-term radioactive waste from making the neutron source to begin with. And that's really why I think fusion is the holy grail.
Is it the size of your neutron source? Like, would that EOS reactor be significantly smaller than the 300 megawatt?
Yeah, that's an interesting point, and I'll try to tackle it quickly. The neutron source stellarator indeed is a smaller system. Part of that is just because of the amount of stuff it takes to stop a DD neutron. A DD neutron, which is either 2 to 3 MeV, you can stop that in about a foot of blanket material. Well, it's a little bit more than a foot, but call it a foot and a half. for a DT neutron, that 14 MeV neutron, there's a reason that DT is, I think, going to be the type of fusion that gets commercialized that produces energy on the grid. Has the lowest triple product, has the highest cross section, and makes a 14.3 MeV neutron, an incredibly energetic neutron. The downside of that, though, is to stop a 14 MeV neutron. If you're using a mixture of lead and lithium, you need 1.2 meters of stuff. That means your blanket is 1.2 meters thick at all points. So if your fusion plasma is here, your magnets can't be in that neutron flux or you'll fry them. You need to have a blanket that's 1.2 meters thick. If you think about just the size parameters of this, and this could be the plasma could be from whatever, I'll just call the fusing plasma. If you have a laser, if you're doing inertial confinement or for magnetic confinement for a tokamak and a stellarator, that sets a minimum system size. You're not going to have a Mr. Fusion just because you need a blanket to protect your fancy parts of the system from the neutron flux. You can't have your fancy parts, lasers, magnets in the neutron flux. That means that any and all DT-based fusion power plants will have a minimum size that's more than a few meters. So absolutely, that for us sets the parameter of that 300 megawatt power plant. And it means that the DD neutron source stellarator EOS will have, call it a 3 meter major radius. So yeah, a decent chunk smaller than the power plant.
And then your rough timeline, I didn't quite get that. So you're looking at that the next year, the year after, what would we be looking at?
So we're doing the prototyping right now. We are alongside the prototyping working through, we had a pre-conceptual design that we put together in 2023. We're taking that and moving it through the next design phases of a number of the subsystems. The goal is that as we show the prototyping milestones throughout the rest of this year, we will then really start to focus on the deployment of the neutron source stellarator. That's something, it's a large scale fusion integrated fusion system. It will take at least a few years to design, a few more years to construct, and a year of commissioning. So that's something that we intend to start commissioning towards the end of this decade. So first plasma at the end of the decade, call it 2029, 2030. And after hitting a number of those performance milestones on the neutron source stellarator, that's when we will scale up the design to the power plant. We're very fortunate here that it is a much more linear growth from EOS, the neutron source stellarator, to a pilot plant. Yes, it's a scaling of size. However, when you talk about the parameters of the core systems, the blanket spacing is around the same size. The planar coil magnets is around the same size growth. So the stellarator is steady state. We have that box checked. We don't really have to deal with how do you go from a small post to a long duration system. There will still be other technologies that you need to fold in because it's a DT fusion. And this is not just for Thea. This is for all technologies that are going from an integrated system to a power plant. You have to deal with a DT neutron flux over steady state operation. For us, that means that we're just going to build a system that you can get to replace the first wall on a pretty regular basis. So you can compute the current material science of the world and the neutron flux in just how short of a time it takes to replace the first wall. It's just a few years. So we fully want to take advantage of future benefits and technologies related to first walls and blankets, but we also want to assume that for the first system, that first of a kind pilot plant that we intend to launch in the 2030s, based on what currently exists. And therefore, we will have a maintenance scheme that we can remove sections as needed on a regular basis, given that it's all these slices. So that system, that scale up of EOS to a pilot plant, that will be in the 2030s.
This is all very exciting. A lot of great innovations that look like are going to, making the conservative engineering choices to get to practical commercial systems. One looks like first with the tritium generator, the neutron source, and then with the power plant, all step by step, where you make something smaller that would already be a very commercially viable system. And leveraging things that, as you say, the magnets and the control systems that are all getting well developed. So it's all
Yeah.
very great.
There's fusion is tough. You have to create conditions at the center of the sun with pieces of hardware. So we're just trying to think through a logical progression of how to de-risk certain engineering components to prove out our technology, and then to take the next step to grow, to build a neutron source stellar, to build a power plant, to go from where we are today to commercialization as efficiently as possible.
So it looks like a lot of things will be happening this year and next year. I look forward to talking more about that, especially when you get your proof of concept on those 3x3 magnets.
Yeah, thanks, Brian.
And
We've covered a lot.
Yeah, we have. Okay, so look forward to talking again. So thank you very
Brian.
much.
Likewise. Take care.
Bye.